All righty, friends. So we kind of turned the corner here. We're kind of um, going to the last part of chapter 3 here. We're actually getting close to being done with um, essentially the first semester topics. Chapter 4 is kind of that get bridge into the second semester. So we're getting close to being the end. And finishing up at least finishing up our last essential skills for this section or this first semester. So we've made pretty good progress. Hopefully you guys are still with me here, doing all right. Let's see what we got here now. Today we're going to talk about something called curve sketching. Okay? Now, if you notice, curves on a graph, they look like that. They're made up of really 4 different types. See if you can actually kind of locate where these types are. So for instance, this one right here, where would that be located, do you think? You're right. You kind of see it here. Kind of see it right here. And that's about it. This one, kind of see it right here. And right here. This one right here comes up right about there and right about there. And then the last one here, oh, I can't use that. Let's try black. This one right here kind of comes up and meets up and finish. Every graph is essentially that's curved, so not straight lines, is going to be a combination of one of these 4 little curves. So what we're going to look at today is we're going to try to figure out how can we use these to interpret what the graph looks like, and then use it to sketch whatever that graph is. So let's start here. What I want you guys to do is I want you to pause the video and see if you can determine what's going on at each of these 3 values right, or not 3, I guess 5 values right here. And then put a little description of what you think it might be. Go and pause the video and do it. All right, so what did you say here? It's critical number, but the first derivative didn't change signs. Critical number, but the second derivative did. So that means that this has to be a point of inflection. So we can interpret what's going on just by some given information. So we have a point of inflection. Notice all these values, these 5 points are essentially, they are critical numbers. Here at -1, 1, it's a critical number. The first derivative didn't change signs. The second derivative did. I'm not going to write out point of inflection again because I'm just going to write point of POI, point of inflection. That is not the appropriate definition. On the AP test, you must write out point of inflection. At 3, critical number, notice my first derivative changed signs from greater than to less than, so it's a relative max. Or I could use the second derivative test and notice a critical number where the second derivative is less than 0. So that makes it a relative max. So I have a relative max here. So somehow when I combine these pieces, this is all going to pop out. At the point 1, 0, I have a critical number. It's undefined though. But the second derivative changes sign, so it's another point of inflection. And at the point 2, -2, critical number, and I have a relative minimum this time. So what we're going to do, then let's go ahead and throw these points on our graph. So we had -2, -2. We don't know what's going to happen between them yet. All we know is that these points are going to be somewhere, -1, 1. And we have 0, 3. We have 1, 0. and we have 2, -2. Okay, so something happens in between all these graphs. Next thing I want you guys to do is I want you to take these 4 curves and figure out which curve is being described here on this domain. So like I'll do the first one together. I see a first derivative that's greater than 0 and a second derivative that's less than 0. First derivative that's greater than 0, a second derivative that's less than 0. It looks like it's this first curve right here. So in other words, when I come to this graph, chances are I have something like this going on. See if you guys can determine what other types of curves we have and put them in the description category. Go ahead and pause the video. All right, let's see how you guys did. This one right here, it's going to be going up like that. All right, this one right here, like that. Then we have where they're both less than. And then we have where it's less than but going up. So that means it's like this. You can kind of see how the little pieces are eventually going to kind of go together here. So let's take it. We already did the first piece. Let's try the second piece. So it's really flat. Kind of comes up. Whoa. Let's try that again. It's a little narrow, isn't it? Okay. And then I'm gonna, the third piece, this one right here, it's going up, and the fourth one, notice how it kind of turns a little bit, but it's kind of cool how these little, we can use what we know now about first and second derivatives to start to help us piece together what graphs might look like. So we end up with a graph looking something kind of like that. And as long as we know what the first and second derivatives are, and we know what these critical points are, we can get a pretty accurate view of what's happening at every single graph. All right, next up. So we can actually go ahead now and play with it a little bit more and start to see how different piecewise functions kind of go together, and how what the first and the graph in the first derivative might look like. So for instance, if we have this graph right here, if I have a constant line, the slope of a constant line is 0. So that means the graph of that f of x would be a horizontal line when it's 0. So again, for instance, this would be like f of x equals some number. When you take the derivative of that, the derivative of every constant number is 0, so kind of makes sense that it would be on the horizontal line. Let's keep going. Let's look at some other ones here. What about linear functions? See if you can figure out why this might make sense. Go ahead and pause the video and consider it a little bit. All right, let's see what you guys came up with. So first of all, this is not this line, but let's just pretend like it is. Say I had y equals x. What's the derivative of that function? That would be 1, which is a positive number. So any positive increasing line, an increasing line would have a derivative, graph of a derivative, that would be a positive horizontal line. So let's, how about this one right here? What if we had a, say that was -2x, that'd be a decreasing line. Take the derivative of it, it'd be -2, so we'd have a horizontal line that had a negative value. Because remember, the derivative is always 1 degree less. All right, what about quadratic type ones? See if these can make sense to you. By the way, I have a problem with this first one. It's off a little bit. So I'll try to redo it, see if we can get it in the right spot. All right, so here at these quadratics, where it changes from decreasing to increasing or increasing to decreasing, that's when our first derivative equals 0. So anytime you see a change of direction, you should have 0. So here's my problem with this one. this graph should have had crossed the x-axis over here. I'm okay with this one. Notice the derivative crosses the x-axis at that point. And then from here, it's decreasing. And if the graph is decreasing, that means the first derivative is less than 0. So if we go down a degree from a quadratic goes to linear, does it make sense then that this graph is below the x-axis? It's increasing, therefore the derivative is greater than 0. So therefore, it would be above the x-axis, and technically this should be right about here. And also notice we're using open dots at the end of these here because these are piecewise functions. Okay, piecewise functions. Graphs aren't differentiable at endpoints. So technically the graph should have been over here where I drew the new one. So again, let's take a look at this one down here. It's increasing on this side. So it goes up. Therefore, I have a derivative that is positive. So this is a positive slope. That's why it's above the x-axis. This part's decreasing. So my first derivative is less than 0. Therefore, I'm below the x-axis. Kind of hoping this kind of makes sense a little bit. We're going to be playing with it here in a second. These are actually, people tend to find them kind of fun. We'll find out if you guys find them fun. Now, notice on this, on the cubic, that point of inflection there, it has a slope, a horizontal tangent line, halfway in the middle. So that point of inflection has a horizontal tangent line. So does it make sense then that it has an x-intercept? The graph goes from increasing to increasing. So it goes from a first derivative that's greater than 0 to a first derivative that's greater than 0. So that means it's going to be above the x-axis the entire time. And it went from steep to narrow. So steep down to our thing, up. So a positive first derivative, just like we had, to a 0 and positive. Why don't you pause the video real quick and see if you can make this one make sense in your mind. All right, let's see what you guys came up with. Did it make sense? Again, we have a flat line. So that makes it a x-intercept, like that. And it is decreasing, friends. So decreasing to decreasing. In other words, it's going to have a derivative or a slope value that is less than 0 and a slope value that is less than 0. So in other words, it went a negative derivative up to our x-intercept to a negative derivative. And we're going to have one other type of little graph that we're going to be kind of playing with as we put this together. We have our cube roots. So see in your mind, go and see if you can figure out why they might look like this. Cube roots might give us this kind of a parabola. Go for it. All right, see how you did here. Notice these are pretty flat right here, right? These are kind of really flattened out. So therefore, if they're flattened out, that means that they would be pretty much x-intercepts because they would have slopes that would be equal to 0. So we have our x-intercept. Now, realize again that these are open dots because these are endpoints. What happens in the middle? I went from increasing to increasing. And it's at its steepest, its highest value there in the middle, that point of inflection. So I'm going from positive. That arrow points to where it was at its highest derivative as it's getting ready to come back to the other flat part. There we go. And again on this one, we have a flat line. And we have a flat line. So therefore, that's why we have those open dots. Those are x-intercepts. Anytime you see a flat line be x-intercepts, and they're open dots because they're endpoints as well. And it went from decreasing, so a negative derivative, decreasing, negative derivative, so that's where the negatives come in. And that part, that point of inflection, that's when it's at its most negative. So right there, it's at its most negative. It starts to turn it together. So here's what we're going to play with today. We're going to try to see now if we can actually take a graph and start to put the pieces together. So on scratch paper or off the side, I want to see if you can try this. So I'm telling you that, notice what I gave you here. I'm giving you the graph of f of x. We are going to sketch a graph of, we're going to sketch a graph of f prime of x. Okay? So why don't you pause the video and see what you can come up with. All right, let's see how you guys did. Notice I got a line. Okay. Actually, let me have you guys pause again. Go back and check. Remember, go back and use the pieces that we talked about before to help you out if you're struggling a little bit. All right, let's see how you did this time. Okay, so we got an increasing line. That means it has a positive slope. So my derivative is going to be a degree lower, and we'll have a positive slope. So, and then I will just put open dots at the end. There we go. This is a piecewise function. It's not going to go together. All right, so the next one I have here, and I'm going to alternate colors so you can see it a little better. Notice I have a flat line, and I have a flat line. So I'm going to have open dots, because those means those are x-intercepts. I'm going to have a parabola that's going to somehow tie this together. And since it's decreasing, then my graph is going to be below the x-axis. Okay. All right, let's have you guys try this one. Let's see what we got here. Okay, notice this is where it changes directions right here. So that means I have a line right there, a horizontal tangent line. So that means I'm going to have an x-intercept there. And since I'm going from an increasing to a decreasing graph, my derivative is going to go from positive to negative. So something like that. And again, it doesn't matter how far I make it go up or down or any of that kind of stuff. All that matters is that I have the gist of it right. All right, what do we got on the next one here? Again, it looks like it's another horizontal line to a horizontal line. Therefore, I have 2x intercepts. And by the way, this one was decreasing to decreasing. This one is increasing to increasing. So that means I'm going to have a parabola then that's going to go increasing to decreasing. All right, what we got here? I have a decreasing line. So that means I have a negative slope. So negative horizontal line. And on this next one, why does the green seem like it always gets the weird ones? Okay, I got a flat line right here, it looks like. Some sort of horizontal line there. Therefore, I'm going to have an x-intercept there. The graph goes from increasing to increasing. So therefore, I'm going to have a parabola like this. And you guys will get more practice today on this on your classwork, but hopefully it gives you a little bit of an idea. Look at this one. I have a horizontal line. Well, horizontal line is great because the slope of every horizontal line is 0 to hero, but that should have been red. Alrighty. Whoop, whoop. I'll play connect the dots on that one. And then last and certainly least, we're back to our green here. We have a horizontal line, which tells me I'm going to have an x-intercept. And then since my graph is going from decreasing to increasing, I'm going to have a line that's going to go from below the x-axis to above the x-axis like this. And again, it doesn't matter how steep it is. Don't worry about that. Just have an idea of what's going on. So you end up getting a graph, a first derivative graph that looks like that. Let me go ahead and erase all the extra stuff now so you can actually see it. So my guess is you're probably had a little trouble with it. And we're going to do more of these in class, so don't worry too much about it. If you struggle with it a little bit, looks kind of like that. So we went from a first derivative. I went from a function and we graphed a first derivative. Notice the first derivative is a piecewise function. The function itself, we start off continuous, but this is a piecewise function. All right, let's keep going here. Now, friends, this time, and I didn't put the word continuous, we're going to make this a continuous graph. So this time I'm giving you the graph of the first derivative. Okay, so this time I gave you the graph of the first derivative. And we're going to sketch the graph of f of x. But even though I didn't include it on mine, I'm going to, by the time you get this, it'll be included. Make it continuous. Make f of x continuous. All right. Use those pieces again that we have, that little chart we kind of made and walk through and see if you guys can actually make a sketch of what this might look like. All right. And again, this isn't necessarily exactly what you see on the AP test, but they will, on the AP test, they'll show you different graphs, and you got to be able to go back and forth between the two and being able to interpret them in different directions, which is essentially what we're doing. All right, go for it. All right, so let's see how you did. I'm starting off my very first one. I have a derivative that is a positive horizontal line. So that means I'm going to have, if that's my slope, that means I'm going to increase. And again, it doesn't matter how high or low you are. All that matters is that you play connect the dots. My next one, I have a horizontal line on the x-axis. That means I have a slope of 0. That means I have a constant number there. So we're now going to make a constant number. Woo. And again, we're making this one continuous. Now I have a negative horizontal line. Negative horizontal line means I'm going to be decreasing. Again, it doesn't matter how much I go up or down. Okay. Now I have this parabola. Remember, every time we see an x-intercept, that's going to be a flat part of my graph. So I'm above the graph, so I'm going to be going flat part. and I'm above the graph, so I'm going to be increasing to another flat part. So I got to somehow connect these flat parts. Those are my x-intercepts are. So this is going to be a cubic. All right, so where this x-intercept is, I'm going to have a x-intercept, or I'm going to have a relative extrema. So is it a relative max or a relative min? We'll look at the graph. The first derivative is negative to positive. If the first derivative goes from negative to positive, that means it is a relative min. So I'm going to go down below. I'm making a parabola then that goes below. So it doesn't matter where I put it. It doesn't matter. As long as I have a parabola, we're good. All right. So I'm going to start here. So where does it? There we are. Notice I only have one flat part. So where I have one x-intercept, that's going to be a flat part. And since it's below, I'm going to make a flat part here where that x-intercept is. Since it's below the x-axis, that means it's decreasing. So I'm going to go from decreasing to x-intercept to decreasing. So decreasing to flat to decreasing. This is a cubic function. So decreasing to flat to decreasing. Okay, so where that x-intercept is, that's where I'm going to have either a relative max or a relative min. I'm going from a derivative that's positive, so first derivative greater than 0 to first derivative less than 0. Greater than 0 to less than 0, that is a relative max. I'm going to have a relative maximum where that x-intercept is. I forgot to change colors. So we're going to go up, parabola, and down. Like I said, you'll be doing more of this on your classwork. We're going to do more in class in general. These are actually supposed to be kind of fun as you put the pieces together. All right, so now we have a x-intercept here. So that's a flat part. So is it flat above or flat below? We'll look at the graph. The graph is above the x-axis. Therefore, it's always increasing. So that means my flat part is going to be up here. I have to increase to it. So I'm going to go increase to the flat part. And then I'm going to increase again to the flat part. Now from there, last piece we got, I have a flat part because an x-intercept. So I know I'm going to be at a flat part here. What I got to figure out then is the other flat part. Is that going to be above it or below it? We'll look at the graph. It's below the x-axis. If it's below the x-axis, that means it had to decrease. So I'm going to decrease, or that means my other flat part is going to be decreased. And I then have to connect the dots to them. So curve it and then bring it together. There we go. All right, I've only got one more problem to look at here, and then we'll call it a day. You guys are probably going, this is a little bit weird. Yeah, I know, it's awesome. I love it. All right, let's see if we can get a little more in here. Yeah. All right, we kind of looked at something like this a little bit before. Oh, I'd really like to. There we go. Perfect. All right, friends, let's see what we can do with this, shall we? Now, I'm giving you the graph. What graph did I give you? Notice, take a look. This is the graph of f prime of x. Okay. This is one of the big things that they love to do to you on the AP test. They give you a graph of f prime of x, not f of x, and they ask you to determine a bunch of information. So we'll see if we can't figure this out together. Why don't you guys pause the video, take a shot at it, and then we will come back and take a look at it. Okay? All right, friends, let's see how you did, right? F of x is increasing. Well, let's think about what that means. If it's increasing, it means it's a positive value. Well, this is my graph. When is this derivative a positive value? It's a positive value here, and it's a positive value there. So that's my increasing. When am I, so that's when I'm increasing. That means I'm going to be we can go ahead and throw it on there. From, what values are those? 0 to 3. Notice I'm keeping it as an open interval, not a closed interval. Because f prime of x is greater than 0. From 0 to 3. Is there a way to make this smaller? No, can't. It's like a one font fits all. So I kind of don't like that. Let's undo that. Let me just go ahead and write it out. It'll be a little sloppy and it'll take a little bit of time, but it'll be a little bit easier, hopefully. So f of x is increasing. I'll just let that be the first part of what I'm writing here. From 1 to 3, or 0 to 3, sorry. Because f prime of x is greater than 0. From 0 to 3. All right, friends. Why don't you try the next one? If you pause it for a second and see what you can come up with. All right, let's see here. So decreasing then, that's when our derivative is negative. So that means it's below the x-axis. So negative, 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 negative. So notice, there's a couple times it hits the x-axis. Those aren't, so they're not going to be values that are continuous all the way through as far as negative goes. So I'm negative from -3 to -2. I do know that this is a continuous function because it is differentiable. I hit 0 at -2, so I'm going to leave that one alone. So -2 to 0. And 3 to, what's that? 3, 4, 5, 6, 7. 3 to 7. Because f prime of x is less than 0 from those values. See, now I can go off the page. There is no confining me, friends. There is no stopping me. So it's going to be important for the next little bit. And 3, 2, 7. All right. Let's go and take a look at the relative max and min next. So relative max, this is when our derivative goes from positive to negative. Positive to negative. Well, that happens right here. Graph goes from positive to negative. So that means that x equals 3. So notice, as of right now, I don't know how to find the y value yet. All I know is how to figure out where the x value is. Later on, we'll know how to find the y value at that point. We don't know how to do that yet. So relative max at x equals 3. I'm only going to use the x value here right now because I don't know how to find the y yet. X equals 3 because f prime of x changes. So notice we're pretty much skipping the say what we're going to do part. And then doing the work, that's just on the graph. We're just pretty much saying what we found. Changes from greater than 0 to less than 0. So now for the relative min, we're looking for when it changes from a negative derivative to a positive derivative. So where'd that happen at? That'd be right there. Notice we have another critical number on here, right here at -2, but the derivative didn't change signs, so it's not any sort of relative extrema. But I do have one here when at x equals 0 because it changed signs there. So at x equals 0, because f prime of x changes from less than 0 to greater than 0. All right. We are writing with a mouse, friends, I tell you what. At x equals 0. All right. So I'm going to have to erase my screen here in a second to deal with concavity and points of inflection. But why don't you guys pause the video now and see how to deal with concavity and points of inflection. Best way to think of it now is if second derivative, if that's the derivative of your first, when would the second derivative be positive? When would the first derivative, or I'm sorry, when would the second derivative be negative? Think about that for a second. We'll come back and talk about it. All righty, so the second derivative is going to be negative when the first derivative is decreasing. Likewise, the second derivative is going to be greater than 0 when the first derivative is increasing. So these are kind of like the big ideas then that we're looking for. So if you need to, take another second here and see if you guys can actually determine when is it increasing and decreasing. Kind of move that for a second so I can erase. You never knew it. All right. So let's deal with concave up. Concave up is when our second derivative is positive. So when is this increasing? Let's see here. You can do this. increasing here. It's increasing here. And it's increasing here. So it's going to have it's going to be concave up at those values, because that is when it is increasing. I could say when it's greater than 0, when the second derivative is greater than 0 there, but this is more of dealing with when they're increasing. So I'm going to leave it at increase. So -3 to -2. I have -1 to 1. And 5 to 7. Because f prime of x is increasing. Since I'm talking about increasing here, I'm not really talking about second derivative values. It wouldn't be wrong to talk about the second derivative values there, but I'm technically basing it off of when it's increasing or decreasing. So that's why I'm sticking with those. So from -3 to 2, from -1 to 1, and 5 to 7. So that means the second derivative is less than 0. It's concave down when my first derivative is decreasing. So by that, we can kind of see where that happens. The nice thing about using the colors here, we can also see where the concavity changes, and we can find those points of inflection too. All right, so it's concave down from -2 to -1. -2 to -1. And 1 to 5. Because f prime of x is decreasing from those values. From those values. And then the last one, friends. When or where are the points of inflection? Where are the points of inflection? Points of inflection is when the graph goes from concave up to concave down, or concave down to concave up. It's when my second derivative changes signs. Well, the second derivative changes signs at here. Turns out I have 4 points of inflection because it changes signs 4 times. So let's write that. At x equals -2, x equals -1, x equals 1, and x equals 5. Because f prime of x changes directions. I could say f double prime changes signs. Yeah, that's probably easier. Well, it's a lot easier, but changes from increasing to decreasing. If I was talking about the values of the second derivative, it'd be a whole lot easier, but that's all right. talking about increasing and decreasing here. So I got to stick with that. From increasing to decreasing. Some of you guys, we were on a whiteboard, a normal whiteboard in the classroom. I would have been done writing this a long time ago. And when you go from increasing to decreasing, that was at -2 and 1. And increase and decreasing to increasing. Just bear with, friends. We almost got it done. Almost got it done. Decreasing to increasing.